bit of 17A derivative warm up for us, and then we'll dive in. So I have chosen these problems specifically because of the types of antiderivative rules we're going to be working with today. So this first one, if I'm going to take the derivative, sorry, it keeps like unfocusing on me. If I'm going to take the derivative, I'm thinking about chain rule. Outside function here is sine. The derivative of sine is cosine. Calculus can never change the argument of a trig function. Whether you're taking derivatives or integrals, what's inside stays the same unless you use a trig identity. So I'm going to have that same x squared minus 3x inside, and then chain rule says I better multiply by 2x minus 3. I took a derivative, not an integral. I don't have a plus c. Just a quick note on that. A lot of people mentioned forgetting the plus c on the quiz last week. So my recommendation, if you're not in the habit of doing that every time you're working through a problem, get in the habit of writing it, even if it's just in your notes, even if it's when you're working homework problems for yourself, write it every time so that it's just really ingrained. Okay. But here we're taking derivatives. I don't need a plus c. This one, I'm looking at a little bit of product rule. So when I take the derivative of something with a product rule, I've got derivative of the first piece times leaving the second piece alone. Addition, because it's a product rule, leave the first piece alone, and the derivative of e to the x is just e to the x. So that's it. Questions about those two before we do more fun things? Cool. So there was a request to do a problem from, did you have a specific homework problem in mind?
It was either, I think it was homework 5, the second to last one.
Okay. So I'm going to do that homework. I'm going to do a homework problem first. The starred one or the one that had the growth rate of a fish population? You got it. Okay. So this is number 3 from homework 5. And it is a little bit gross, not gonna lie. So the thing that we are told is that the rate of growth is given by this function, and I'm going to try to get all my zeros in here. This is a 60,000 e to the negative 0.6t all over 1 plus 5 e to the negative 0.6t whole thing squared. And I'm gonna start this now and then finish it later. And here's what I mean by the start this now. Let's get the setup going, but I'm not actually going to integrate the thing just yet. So if this is the growth rate, then we've got a net change theorem in the textbook, but we can also just think about this from a fundamental theorem of calculus perspective. This thing is how much the biomass is changing. And if I'm looking for that cumulative change says I'm adding up a bunch of little bits, and an addition problem is called a sum, and we can write a summation problem using this cool big S thing. Which means I'm really looking for, and we wanted the predicted biomass in 2020. So I'm really looking at this as the starting biomass plus the cumulative change. Cumulative change part. And we were given a starting biomass of 25,000. And then that cumulative change is going to come from us looking at that growth rate from 0 to 20. And the reason it's 0 to 20 is because it says T is years since 2000, which means T equals 0 corresponds to the year 2000, and T equals 20 would correspond to the year 2020. So that's really our goal of what we are trying to evaluate. Here's the thing. In order for me to evaluate that, I'd really like to use a U substitution, and we haven't talked about that yet. So I'm going to pause this for a second, and we will return back to it after we spend a few minutes talking about U sub. So I promise I'll return to it. Oh, quick question first. Yeah.
I know this is like a difficult way to do it, but could we do it using integration of parts? Or is U substitution the way to go?
There is likely a path through this with integration by parts. It is not what you should do. How about that? Yeah. Okay. I am going to flip this page, but I promise we're coming back to it. I just want to make sure that we have plenty of space. Okay. So we are going to spend some time building different techniques of integration. But all of those techniques of integration, remember, we're thinking about antiderivatives. So really our go-to starting point is always, can I make this look like a number times x raised to a power? And when I can't do that, the very next question that we want to ask ourselves is somebody's derivative sitting inside of that problem. And that is what tells us we should be doing a U substitution. And that's my go-to every time. And only when a U substitution fails, am I trying something more complicated. So here, let's talk about U substitution. I'm going to give us a problem to do here. Trying to decide how fun to make this problem. I'm going to make it not terrible. Yeah, I'm going to make the first one not terrible. Okay. Given time, energy, and sufficient monetary motivation, how many people could multiply that garbage out? You could. How many people don't want to? Yeah, me either. I really don't want to. So I'm going to walk up to this integral and I'm going to say, well, I could make it look like x is raised to powers, but I'm not going to. The very next question I'm going to ask myself is, does the derivative of one part equal the other part? And the answer to that question is yes. Here's how I think about U substitution. Does anyone have a language that they've always wanted to learn, but they've never taken the time to do it? What language?
Well, the sign language too.
So, absolutely. ASL. Does anyone sign? Okay, we should all like make a pact. We're learning ASL. Okay. So it definitely counts. It's going to be difficult for my example, but I'm going to try for it anyway. Okay. I imagine that if we were all taking a sign language class, we wouldn't necessarily have a dictionary, but there's probably some sort of visual cue card that would show us hand signals for different words, right? So what I think about a U substitution, I'm saying someone just asked me a question in a language I don't know yet. So what I'm going to do is I'm going to look to my dictionary so that I can translate that question into something that I can work with, answer the question in the language I can work with, and then go back. So someone just signed something to us and my brain is like, okay, I got to slow that down. I need to look at the cue card that's going to tell me what those signs mean. So I'm going to come off to the side and build a vocabulary list. I'm like building my dictionary over here. So I'm going to look for the part whose derivative is sitting in the problem. And I'm going to call that part u, x cubed plus 4. And now I'm going to build my vocabulary list. Well, there are other things in the problem that I'm going to have to translate. Oh, yeah.
Would it include the like 7?
Nope. I'm only going to take the part whose derivative is in the problem. Now I'm going to build my vocabulary list. And the way I'm going to do that, I know I'm going to have to translate that dx. So I'm going to take the derivative. I'm doing it this way once and only once. I'm not writing it this way again, but I'm going to take the derivative. And when I take the derivative of the right-hand side, I get 3x squared. That is true and correct, but it's going to slow me down to write that step out. Because the very next thing that I want to do is really, I'm going to multiply both sides here by dx. And in the future, I am going to skip that middle step and just come straight to here. Because I'm going to need to do that step every single time I'm doing a u substitution. Now our goal is that this is my vocabulary list to translate everything in the problem. So if I come over here, this portion becomes u raised to the 7th power. And the 3x squared times dx, I have that in my vocabulary list. So I get to translate that entire thing into du. Now that I've translated into something that's easier for my brain to work with, now I can find the antiderivative. So the antiderivative of u to the 7th is going to look like add 1 to the exponent, divide by the new exponent, plus a constant. But if we were in an ASL class, I'm not expecting to get to tell the teacher my answer in spoken English. I'm going to have to translate that back to the language the question was asked in. And so the language that the question was asked in is the language of x's, and I'm going to translate that back to the language of x's. So this is going to become x cubed plus 4 to the 8th over 8 plus a constant. I will warn you that a u substitution is not always this convenient. The derivative is not always just sitting perfectly there for me in the problem. So let's do some examples that we have to work a little harder. I have an integration problem. I'm going to walk up to it and I'm going to say, can I make this look like x is raised to powers? And I really can't because of that addition on the bottom. I can't just break this up as separate fractions. So I'm stuck. But the very next question I'm going to ask is, does the derivative of one part equal the other part? Kinda. That's what's cluing me in about a u substitution. Also, sometimes u just stands for ugly and you pick the ugliest part. I'm not kidding. But in this case, I'm thinking about, well, if I take the derivative of the bottom, I'm going to have something that looks like an x plus a number. That's what I'm going to build my vocabulary list off of. So if u is equal to x squared plus 4x, then I know that du is 2x plus 4 times dx. The whole point is to build a vocabulary list to translate everything over here. I'm not quite there yet because I don't have a 2x plus 4. So I'm going to divide both sides of this equation by 2. And I'm going to say that du over 2 is equal to x plus 2 dx. Which means that when I go to translate this, I have a u on the bottom, but all of that stuff on the top is a 1/2 du. And it's up to you if you want to put the number out in front or not. I kind of prefer to put the number out in front to say that that's 1/2 of 1 over u du. And now we're ready to find the antiderivative because it's in a language we can deal with. Whose derivative is 1 over u? Yeah. So this is going to look like 1/2 natural log absolute value of u plus a constant. And my same final step here, I'm going to have to translate that back. So 1/2 natural log absolute value x squared plus 4x plus a constant. Yeah. Oh, so I'm being careful with the absolute value. Whenever we take the integral of 1 over x, we should generally include the absolute value unless we know from the bounds that we'll only be dealing with positive numbers, because we want the domain of 1 over x to match the domain of natural log, and it doesn't. Because 1 over x, I can plug in negative numbers or positive numbers, but I can't for natural log. So the way we correct for that is to put absolute values on when we take the antiderivative. There was another hand though. Yeah.
Where did we get 1 over u?
So when I do my translating, the top of this, the x plus 2 dx, that translates as du over 2. But the x squared plus 4x is in the denominator. That's what we called u. So it's got to be in the denominator there. And then I just took the 1/2 out in front. Yeah. Does that help? Cool. Yeah.
So what is this? What's your strategy for choosing which one should be used?
So anytime, and I will tell you, the strategy is going to be different when we do integration by parts. So for u substitution or just substitution, I am choosing u based on which function has its derivative in the problem. Now, if everything is polynomials, that means your u is the one with the higher degree every time. It's not always that obvious. So let's do some more to practice finding what that u is. I think I can squeeze one more in here. So I'm going to walk up to this and say, can I make it look like x is raised to powers? Well, definitely not, because I've got exponential parts in there. Also, if this had been flipped over, I wouldn't do what I'm about to do. But it's not. I have 2 pieces on the bottom separated by addition or subtraction, which means I can't break this up into separate fractions. And if I can't break it up into separate fractions, I'm asking myself, does the derivative of one part equal the other part? Now, the other way to think about u is which part looks a little more complicated. And the bottom looks a little more complicated. So I'm going to build my vocabulary list by letting u equal 4 minus e to the x, which means that my derivative is negative e to the x dx, which is almost what I have in the numerator. I'm just off by a minus sign. So if I multiply both sides by a -1, I've got negative du is equal to e to the x dx. So I can take the entire numerator and call that negative du. And the denominator is just a u. And when I translate that, that means I'll have 1 over u and then a negative du. And I put my negative sign out in front. It's totally fine if you just put it on top with the -1. I know I gave us another natural log. Yeah.
Oh, could we technically put e to the x as u and then do it? Cause like then we don't have to like multiply the du by a -1.
So that's a really good question. So let's play the what if game. So what if we made u equal to e to the x? So if I made u equal to e to the x, then du would just be e to the x dx. So now I'm going to think about how I would translate this. So now my numerator would just be du. That's fine. And my denominator would look like 1 over 4 minus u. I have a problem with that. What's the antiderivative of 1 over 4 minus u? I heard like 3 different answers. I will write the correct one. And if you can correctly find the antiderivative of this in your head, then this is totally an option. But the correct antiderivative of this is negative natural log of 4, absolute value of 4 minus u. I think this one's easier to find the antiderivative of. So my choice would be to go this route and then have negative natural log absolute value of u plus a constant. And when we translate these two back, they'll be identical. I know people, well, I know that it is often frustrating if there are multiple correct paths through something. There are sometimes multiple correct paths through a u substitution, but I think there is more room for forgetting to do something over here. I think there's room for forgetting that I've got to deal with that minus sign. I think there's room for forgetting to include the 4 minus u part. So I think this is less prone to error. More fun with you, Seb? Okay. I want to show you a couple of u substitutions that are really common and are sort of hiding. So I've got the integral of e to the square root of x over square root of x dx. I'm still gonna like take a minute to think, oh, can I make that look like x is raised to powers? But I'm stuck because of the exponential piece. So now I'm gonna ask myself, hey, does the derivative of one part equal the other part? And maybe I don't see it at first. And if I don't see it at first, I'm going to fall back on, well, let u stand for ugly. What's the uglier part of this? So I'm going to try letting u be equal to root x. I mentioned this at the beginning of the quarter. There is a reason that I have this derivative memorized the way I have it memorized, and it's because of u substitution. If I need to take the derivative here to build my vocabulary list, I might need to think about that root x as x to the 1/2 power, which would make the derivative 1/2 x to the negative 1/2 power. But that's not useful in my context over here. So I have the derivative of square root of x memorized as 1/2 root x. These are equivalent, but this one helps me see it in the u substitution better. So I almost have this. It's just that 2 is in my way. So I'm going to multiply both sides of this by 2 to get 2 du is equal to 1 over the square root of x dx. And I can translate all this stuff now. So this part becomes 2 du, and that e to the square root of x on top is just e to the u. And I'm going to go ahead and pop my 2 out in front. And I will let you finish the integrate and translate back. The integral of v to the u is just e to the u. So I'm going to get 2 e to the u plus a constant. And then I will translate that back to be 2 e to the square root of x plus a constant. We could do u substitutions all day, but I know y'all have a lot of homework problems on it. So hopefully you're getting plenty of practice. But I am going to show you, let's do one more kind of semi-common-ish thing that shows up with u substitutions. If you tried various things for the u substitution, it happens. And sometimes that's what's going to happen on a quiz or an exam, and we just have to try things and work through it. The thing that the function whose derivative is secretly in the problem is x to the negative 3. Because when I take the derivative of x to the negative 3, I'm going to get negative 3x to the negative 4, which can be written as negative 3 over x to the 4 dx. And I've got the dx and the x to the 4 in the denominator. The only piece I don't have is the negative 3. So I would divide both sides by negative 3 or multiply both sides by negative 1/3. So I would say negative 1/3 du is equal to 1 over x to the 4th dx. And that's my vocabulary list that's going to let me translate things. So that whole thing is going to become negative 1/3 du. And when I translate this, I'm going to have secant squared of u times negative 1/3 du. And because that's a constant, I'm going to go ahead and pop it in front of my integral and have negative 1/3 the integral of secant squared u du. Now, this is the place where I don't have a route around it. You have to memorize the derivatives for the trig functions because this is not a u substitution. Please don't try integration by parts on this. It will get worse before it gets better. Secant squared is already somebody's derivative, and we need to just know that. Whose derivative is that? So I'm looking at negative 1/3 tangent of u plus a constant. And that means we've got negative 1/3 tangent of x to the negative 3 plus a constant. Questions? Yeah,
So it's 1/3 because you divided the du by -3, right?
correct. There are other ways to deal with the -3. This is consistent with how the textbook deals with it and consistent with how Shalinor deals with it. If you have had calculus in a previous life, there are other correct ways to do it. I'm just gonna try to make it so you're not seeing different versions. Okay, I am ready to go back to that question from the homework. Armed with u substitution, we are gonna make it through. Oh, actually, there's a really great question in the chat, and so I want to address that. The really great question in the chat right now is, what the heck happens to the du when you find the antiderivative? And the way that I think is easiest to think about it is that essentially this integration symbol and the d something at the back are instructions that say, find the antiderivative of what is in between us. So once you've found the antiderivative, I don't need the instructions anymore. I don't need the integration symbol and I don't need the du, because those are telling me find the antiderivative of what's in between us. And that's really what that part of the fundamental theorem of calculus said. Yeah. Okay. Rolling back in time, going back to problem 3 from homework 5. I hope I have left myself enough space on the page. I think I have. Okay, I've got to integrate that mess. So I'm going to ask myself, does the derivative of one part equal the other part? And the answer to that question is yes. So I'm going to build my vocabulary list over here. I'm going to set u equal to 1 plus 5e to the negative 0.6t. And when I take that derivative, the derivative of 1 is 0. This is going to be 5 times negative 0.06. I'm going to write the 0.6 as a fraction because I don't personally do well with multiplying decimals. So I'm going to write this as 5 times negative 6/10 e to the negative 0.6t times dt. 5 times 6 is 30. 30 divided by 10 is 3. So that means du is equal to negative 3 e to the negative 0.6t dt. And I'm going to go ahead and say that means negative 1/3 du is equal to e to the negative 0.6t dt, so that I'm ready to translate this question. Now there's another piece to translate. And this one's a little bit subtle, but back to that idea of what happens to the d something, dx, dt, du notation. The way this is written, that 0 corresponds to t equals 0. And that 20 corresponds to t equals 20. But when I write the u substitution and I translate this to the language of u's, I also need to translate the bounds. So when t equals 0, u is equal to 1 plus 5e to the 0. Or 6. And when t equals 20, u is equal to 1 plus 5e to the, I'm doing math in my head, negative 12, 60% of 20, it's 12. Obviously, I'm trying to do this without a calculator. If this was a homework problem, you could put that into a calculator, turn that into a number. I don't have a calculator, so I'm just going to drag that ugly thing around. So when I translate this, I've still got that 25,000 out in front. But my integral part becomes 60,000. The e to the negative 0.6 t dt becomes negative 1/3 dt. And on the bottom, sorry, not dt, du. We're translating this to u's. And on the bottom, that's u squared. And then my limits of integration, the t equals 0 was on the bottom, and that corresponds to u equals 6. And the t equals 20 was on the top, and that corresponds to whatever that would be if you put it in a calculator. So 1 plus 5e to the negative 12. Now I'm ready to find the antiderivative. But maybe I want to clean up the numbers a little bit first so it's easier to look at. Can't do anything with that 25,000 out in front yet. But I can multiply 60,000 by negative 1/3 and get minus 20,000 times the integral from 6 to 1 plus 5e to the negative 12th. Now 1 over u squared, that antiderivative is not natural log. Because 1 over u squared is the same as u to the negative 2. And we can take that antiderivative by adding 1 to the exponent and dividing by the new exponent. So I've got 25,000 minus 20,000. When I take that antiderivative, I'm going to get negative 1 over u. And we're evaluating that from 6 to 1 plus 5e to the negative 12th. When we have a definite integral like this and we're doing a u substitution, we're not going to translate back to x's because we already translated what the endpoints are. So if I've already translated what the endpoints are, translating back is doing extra work. I'm just going to plug in those endpoints. So I would have 25,000 minus 20,000 times, we plug in the top, minus we plug in the bottom. Whatever that is.